In section 5, we talk about properties of logarithm function. And this is where most people stumble. Because if you take a look at the list of properties, nothing makes sense. Nothing makes sense. If you skip all the way through this. Wait, why is log of the product is a sum of log? Why is log of division is a minus? Why is log of m to the b? You can somehow throw b out of the parentheses. Why can you split this log into two numbers and add a random number as a new base? Nothing makes sense here, to be honest. But of course, usually these properties are more difficult than the basic properties. For instance, if you have if you have a plus b and you compare that to 1 over a plus b, you can see that you cannot just split them into two fractions. They are not the same. There are several reasons for that. So that means you cannot split the division in the same way as you split the multiplication, or just just the plus or anything like that. Or you cannot have this property. This is not true. You cannot just switch the order of subtraction, because this is actually a minus b minus c, and the later one is a minus b plus c. So once we get to the reverse, then things kind of fall apart. To give you some idea on why this doesn't make sense much. But to make sense of what we have over here, all these properties, we have to go back to the definition of exponential and kind of walk back to the logarithm. We have to derive that from what we already have. For instance, we have m to the power 0 is 1. And that means we can conclude that, okay, keep 0, keep 1, and then move m to the other side to get this property. This implies that, because recall that this means we raise m to the power of 0 to get 1. And so this property immediately gives you the property for the logarithm, which is that log of any base of 1 gives you a 0. That's done. That's the first one. That's the easiest. I think this is the only easy one. So let's see what about the other. So here we have this property. Again, if you think about this as repeated multiplication, okay, there are a copies of m over here, there are b copies of m over there. When we combine them, we get a plus b. But when we turn this into logarithm properties, it gets slightly messier. So let's say the way we do this is we let m over a to be x and m over b to be y, so that we get x times y. Let's x times y on the left. And then what about the right? It's a times b, a plus b. But how do you get a plus b from here? Maybe you can get a plus b if x times y is on x times y on the left, and then you can get a if you apply the logarithm function. So again, a and x stay the same. That gives you the log base m of x. So m to the power of a is x. So this is what we have here. And then likewise, you can get the value of b by using the logarithm. It's going to be log base m of y. So what do you have here now is that we have m to the log base m of x plus log base m of y. And on the right hand side, maybe I should move that. I should actually move that. Okay, let me rewrite that. So this is x times y. This is m to the power of log base m of x plus log base m of y. We add two components together. But this doesn't quite work yet because we still we still have to do some math. But you can see that this is difficult to see, but so we have some number equals to m to the power of another number. So we can kind of repeat the logarithm because we want to bring this whole thing down. We want to take this whole thing down. So what we do is we translate m and make it a base. And now everything is down. So again, if you read that, it means that m to that power is x times y. You take log on both sides, and this becomes log base m of that. Like this becomes just the exponent. And so you end up with this equation. In the left hand side, x times y, and then we take a log to get this from the right hand side. We have to extract a and b individually to get log base m of x plus log base m of y. And this is the most important property of logarithm. Again, maybe let me rewrite that. The log base m of a product. And again, it doesn't make sense if you just look at it at first, but you have to juggle things around to see. So it's log base m of, sorry, let me just go back to x and y. Of x and y, log base m of x plus log base m of y. This is how you prove that. And if you go back, and if you trace back step by step, you could see that this is a, this is b, and this is the power that you need to rest on the left. And so this is what we have for the first, and again the most, maybe not most important, but the most used, let's say, most frequently used properties for logarithm. In a sense, you kind of split. You have log base m of a number of a product. You can split that into twos, and the way you split is you use the addition, and this addition comes from the property of the exponential function. So that's the first property. That's still not too difficult to prove, but again, if you just look at this formula first, nothing makes sense. But it makes sense once you go back a step. Oh, and also I should also note that the product x and y comes from this product. So it's a product from this left hand side and the addition from the right hand side. And so you can draw some analogy for these two properties. Okay, next one. Yeah, division works similarly. If you replace b by minus b, we get this property, right? And And yeah, on again, if you let this be x, if you let that be x, but let that be y, let m to the b be y. Like this would actually give that m to the minus b is actually 1 over y. So we flip that. So now the left hand side sorry becomes x over y. Alright, let me do it step by step. This is x times 1 over m to the b. Maybe this better. And we define m to the b to be, we remove that, to be y. And so that becomes x over y. And likewise, the right hand side is m to the log base m of x minus log base m of y. And once you tidy things up, I take the log base m. I use the definition to take the numbers down. You get this second property. If you, instead of multiplying, we use the division. Like we simply replace that plus by minus. And again, this plus comes from that. And the division actually comes from this. If you write this way, m to the a over m to the b. And then this is where the division came from. So that's the second one. And usually it depends on how often you use this kind of properties, but usually we will combine the first one to the second one, right? Because if you just combine that, you would get log of m of x times y. Okay, sorry, let me skip that because it's going to take a while to explain. And actually, that's going to take another property that we will discover later to explain. So let's keep that for now. The eraser that doesn't work anymore. I think it's tired. Okay, let's move on to the next one then. Oh, never mind. The whole thing doesn't work. No, not sharing. Eraser. Okay. So that's the second one. The next one we have. We use the property we just discover, or we just prove, right? And see what happens if the two numbers are actually the same. So let's say if a and b are the same, what we would have is log base m of a times a equal to log base m of a plus log base m of a. So this is what I have. The left hand side is log base m of a square, and let me emphasize the square. And the right hand side we have two copies of log base m. And we add two copies of the same number, so we get twice the number of logarithms with 2 times log base m of a. So yeah, that you can see how these patterns go, right? If you have 3 copies, or you have a to the third, then you can kind of see that we can split this into 3 terms. They are all the same, so you get 3. And that implies log base m of a to any power of k is equals to k times log base m of a. So this is again, this is just an observation. We didn't prove it. We just observed that if we put the same number, a times a, you get log base m of a plus log base m of a. So we get 2 copies of that. So there should be like that. But to prove that, we have to rely on, again, back to the exponent. So let's say log base m of a is x, and that implies m to the power of x is a. Right, and on the left hand side we want a to the power of k. Right, so what we can do is we can raise both sides of the equation by to the power of k. Now a to the k is m to the x to the k. And this one we can use the property of the exponent to see that it is actually x times k is equal to a to the k. And what this implies is that now we can translate this back to the logarithm. X times k is log base m of a to the k. I move this m to the other side. Okay, so again it means x to the power of m x times k. Sorry, m to the power of x times k is a to the k. Right, but what is x? Go back here and you can see that x is, at the start we define x to be log base m of k. And so this is the proof. We need some observation first to see whether it's true or not. And then make sure that we are doing some careful work to prove the things on the properties, I mean. So that's the property for for the power. And that's why when you have a power, you can pull it down on outside the log, because there's some mechanism behind the scene where this is true. Oh yeah, and finally we have this one. And let me try to recall what that means. Oh yeah, it means if we let m to the a to be x, and then we have x to the b equals to m to the a times b. And that gives us a times b equals to log base m of x to the b. Let me take a look at my cheat sheet, what I meant by that. Oh yeah, correct, that's correct. We'll let x that be that. Oh yeah, and then let y be, actually let y be m to the a to the power of b. And so let y be the whole thing, so we can write that as just a y. And so y is the whole thing. And here we can see that we've moved this. Okay, m to the a is x, implies that we can take log of m, like get the base down to get there. So we get log base m of x equals to a. But what about b? If we repeat that here, we can see that b is log base m to the a of y. Log base m to the a of y. But m to the a is actually x, so it's log base x of y. So we have b now, and so we can just write b over there. And that's the last property, which again doesn't make sense if you just look at the logarithm. You have to go back to the exponential to see how this works. So what this means is that it's kind of like a chain, in the sense that, okay, to find log base m of y, you can find log base m of x, and then find log base x of y. And so that's like a stopping point. Like, maybe like y too far. Like to go from m to y is too far. So you go from m to x, and then from x to y. Kind of like that. And that's the final property. But This is one way to write that. This is one form. Another form is that if you move things around a little bit, so you keep log base m of y on the left, and then divide this orange term, which is log base m of x. The answer is log base x of y. So the same property, but we interpret it in different way. In a different way. And again, what this one, it kind of have the different meanings. It just said, okay, to find log base m x of y, we can introduce a new m, add two new bases, and then compute them separately. And actually, this is very useful. Like when we think about this term, like because for instance, sometimes you are asked to find log base 3 of 4, which is, if you have a calculator, you can input everything inside that. But sometimes you don't have a calculator, or maybe you are given just a table of log base 2, for instance. Or maybe somehow you have log base 2 for all the integers in your mind. And so what we do here is we translate that into, the base that we are familiar with, which is base 2. So that means we can, if you hate base 3, translate that using a different base. And hopefully, this will be in the table, or this will be easier to compute, or maybe, more natural. And also in the future, I think maybe soon, soon, is that usually we mathematicians use log base e to compute things. And just make a note that for now though, that log base e is ln. Where e is a special constant, like e is about 2.1718. It is approximately 2.17. And this is used a lot, so maybe it is better to, to convert the base of log that we don't know or we are not familiar with into ones that we can work with. So these are all the properties and all the proofs of them. And to recap, these are the 5 properties that kind of mimic the 5 properties of exponential functions that we already had. Let's use it a little bit, shall we? So use properties to simplify the terms. There are 4 questions, so let's do it. So the first question we have log base 2 of x plus log base 2 of 32. Like, you have to go back and see which one applies here. Like, but you can see that it's first you see the plus sign. And whenever you have a log with a plus sign, then you should use the property that multiply the numbers inside together. So here you have x times 32. And actually, if you see the numbers on the left, you might wonder why don't we just compute them? Because they are easy to compute. Like, okay, this is 3, this is x, so 3 plus x is, this is 3, this is 5, so 3 plus 5 is 8. But again, just for the sake of, illustrating the properties, using numbers that are simple. So we get that, and now we can reduce that to a single log. So that's 256. And then you can, find 2 to the power of what gives you 256. And the answer is 7. Actually 8, sorry. It said 8. So the answer is 8. Using the plus to combine them. Now for B, this might be a better example because we have log base 3 of a number that we don't recognize. We have 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So you can see that if you are given these numbers, 36 and 4, the numbers are gonna be ugly. Just use the word ugly because I have lots of decimals. But luckily we have this subtraction, which means we can actually combine them first before we compute. And this subtraction, it provides the division. I should also change that to multiplication. And coincidentally, 36 over 4 is 9. So we can compute that immediately. The 3 to the power of what is 9? The answer is 2. That's B. What about C? C is again, we have log that have ugly bases. If you do it one at a time, if you compute the top one, compute the bottom one. Actually, let me do it for you. So if you don't know about properties of log, let's say a equals to log base 5 of 81, and then b equals to log base 5 of 3. Oh, what do I do? Of 3, then a will be, oh nice, it's 4, which it is impossible to see from these numbers. Wait, why is 2.7304 divided by 0.6826 is 4? Now again, that doesn't make sense. But the way you do this is, I use the property that, if you have division of logs and they share the same base, then you can actually translate that into a single log. And this, again, is 4. 3 to the power of 4 is 81. So that's B. And lastly, we have D, like log base 5 of some number. And again, this one, you might have to use several properties. Actually, that's one, but let's do it one at a time. This one doesn't give you a nice number, but you can simplify that. Make it easier to, to at least to put into your calculator. So first, we have an inverse, so 1 over something. So the first step is to flip it up to be a negative, to some negative number. And then we can use the property that, if you have log where the inside is something to the power of something else, then we can put it off, we can throw it away to outside of the log. This log is 5 of 2. And actually this is all you can do. Because log base 5 of 2 is, first it is simplest, and second is there's no way to reduce that further. And this might be a good time to use a calculator. So -4 times log base 5 of 2 by -1.722. So that's the answer. But you are welcome to keep the log if it doesn't spark joy. Just keep the log, don't calculate. But again, compared to, if you have to type 1 over 2 to the 4, it gives you the same result. But, it takes a little bit more time to type. And it looks ugly when you write it on paper because it takes 2 lines. Unlike that, which takes 1.5 line. So these are the logs for you. I think that's all the properties. And one not decide to die, to shut itself down. I think that's a good time to stop. There are actually another section, but I don't think we get enough time to go over. So that's okay, that's it. That's the end of the class. One last thing about some conventions. Whenever you use something a lot, people tend to abbreviate things. And there are two different things, or two different ways people abbreviate. First, if you don't use if the log is written without any bases, we assume that it's base 10. Because again, base 10 is used a lot. And it's used a lot, so let's make it the default. the default version of the logarithm function. And so these two are the same. And so whenever you see like log of 2 plus log of 5, you can assume that, oh, actually it is the author doesn't meet the base, but they use the convention, use the agreement that no base means base 10. Then you can, do some maths. Log base 10, log 10, which is 1. And second, and I mentioned it a little bit, but there's a special base. Base 10 is special. It's used a lot in science and in the scientific notation. But another base is also important in math, physics, and statistics. We use the base E. E is something special. It's a special number. It's about 2.17, just like pi. Pi is defined as the ratio between the circumference of a circle to the radius, not radius, but the line, 2 times the radius. Likewise, E is defined as the rate of something that we don't have enough knowledge to fully understand what it is. But if it doesn't have a base, and if it is written as Aranian, we read it as ln, which is kind of weird. But ln, it actually stands for log. I passed the word natural. I think it was from French, so they put the word log before natural, like not natural log, not the other way around. But anyway, it's ln, it's ln, and this is equals to log base E, base of this special number. And if you go to the calculator we have, it knows what it mean by log of that. Yeah, log base E of ln base E of E is 1. Oh, and also I think, yeah, the calculator also use this convention. If you don't put a base, it means it's base 10. And so that's going to be useful later on in class. Yeah, there's a note there, but for some reason, like people don't agree on things. Like math people and most people in science use log base 10 to represent log as a default, but computer scientists use log base 2 because of bits and digits. If you count how many digits or how many bits do you need in this program, you use base 2 to count. That's something. And yeah, that's the end of the properties of logarithm. We have an application, but I don't think we have time to go over it. So, yeah, that's exercise 2. Finish that, and I will see you next week.